I'm an assistant professor in the Department of Mathematical Sciences here at Seoul National University. I did my Bachelor of Science degree in physics and electrical engineering at the California Institute of Technology. And then I continued on to study at Stanford University with a master's degree in statistics and a PhD in computational mathematics, applied mathematics. Then I worked as a assistant adjunct professor in the UCLA math department, and then I joined SNU in 2020. And my current research interests are optimization, optimization theory, particular convex optimization, and also deep learning theory. So the talk that I'll be giving is titled Neural Tangent Kernel Analysis of Deep Narrow Neural Networks. This is work published in this year's ICML. It's joint work with Jungmin Lee, Juyong Choi, and Albert No. So let me quickly outline the talk. So first I'll have two separate sections outlining preliminaries, trying to motivate why it is that we're doing what we will be doing. So first I'll talk about the training dynamics of deep neural networks via SGD. Then I'll talk about the past theory of neural tangent kernel and universal approximation theory. And then finally I'll talk about this work, the NTK analysis of deep narrow neural networks. Okay, so first let's start from the very basics. So we'll consider the setup of deep supervised learning. This should probably be familiar to most of the audience. We'll consider the setup with data points x1 up to xn. So we have n data points, and we have corresponding labels y1 up to yn. And the canonical example of this is that xi is an email, and then yi is a corresponding label indicating whether the email is a spam email or not. And the goal is to train a neural network H, and here H is a neural network that predicts the label of X, not theta, so this is a typo. And the neural network is parameterized by a parameter that we denote as a theta here. So here's an illustration of a deep neural network. I'll actually just skip this. The point that I wish to make here is that training in deep learning can be viewed as an optimization problem. So when we train a neural network H, we usually solve an optimization problem of this form. So there is some sort of neural network H, and then we provide as input data point xi, and the neural network is to output a prediction of the label yi. And then we have a loss function, here denoted as small script l, which compares the output of the neural network against the true known label yi. If the prediction is accurate, then the loss value will be small or 0. If the prediction is very inaccurate, then the loss value will be very large. We take the sum of such output loss values for all n data points. We take the sum of all such of n data points, and then we take the average. And the goal in solving this optimization problem is to find a parameter theta that makes the neural network H to be best at predicting the known labels. And if the neural network is good at predicting the known labels, then perhaps it can also do a good job at predicting unknown labels as well. For notational simplicity, we'll just write fi to be equal to the loss function that depends on the data point xi and yi. And then now training becomes the optimization problem of finding the minimum of the sum of n functions f1 up to fn. And remember, the data points and the labels, the x and the y's, these are fixed problem data, and theta, the neural network parameter, is the unknown quantity that we wish to find through optimization. It's the quantity that we want to find through training. And the training is done via stochastic gradient descent or some sort of variant of SGD. So the stochastic gradient, abbreviated as SGD, solves this optimization problem through this very simple iteration. So this one-line equation is wrapped around in a for loop. So we'll have a for loop with for loop index k. And at every iteration, we'll select a random index ik. So ik is a random index, it's a random data point. And we select that corresponding data, we compute the loss with respect to that data point, and then perform a gradient descent step with a learning rate alpha. And essentially all modern deep learning setups use SGD or variants of SGD. So plain SGD, as is also now used quite often. Optimizers like Atom and RMS prop are also used very commonly. SGD with momentum is also used commonly, but SGD, the basic form is still a relevant object of research because SGD as is it's used, and it serves as the basis of understanding other optimizers as well. So I'm a mathematician, and I want to understand when does SGD converge? Because we all know that SGD works very well. We all know that deep learning works very well. So the empirical success of deep learning is very clear. So the training must be working in some way. So why does it work so well? Well, if we view training as an optimization problem, when the functions are convex, then there's a lot of very rich and mature theory. There's so much we can say. We can establish convergence rates. There's a lot one can prove, and I myself, as a researcher in optimization, in convex optimization, I've written many papers assuming functions are convex. But the thing is, in deep learning, functions are not convex, and therefore, the assumption of convexity is at best a theoretical interest. It's still, I would say, a little bit relevant, but we can't just assume convexity and declare the problem to have been solved. When the functions are not convex, we can still establish that the training dynamics converges to a local minimum. And roughly speaking, here's how one can carry out the analysis. Here's how one can carry out the proof. This is an outline, a template as how to carry out these analyses. First, we quantify the progress by how much the function value, the loss value, is reduced. After all, the goal is to minimize the loss value. We want to solve this minimization problem, so we quantify with the function how much progress we have made. And then we recognize that SGD reduces the function value in expectation. And in most machine learning, deep learning applications, the loss values are usually lower bounded by value 0. Usually loss values are non-negative, and therefore the optimal value is non-negative. It's lower bounded. So that means SGD cannot reduce the function value forever, and that will necessarily mean that the iteration converges in some sense. And here's an example of in a certain sense, the state-of-the-art mathematical theory on the convergence of SGD. And it states that if SGD is applied to, it uses a square summable but non-summable step size, so the learning rate decays at a certain rate. And if we apply SGD to the class of so-called tame functions, then SGD almost surely converges to a stationary point. And I won't bother to define what exactly I mean by tame functions, but all neural networks are basically tame functions. Tame functions are built with smooth or piecewise smooth functions. So if your neural network uses the ReLU activation function, it's not differentiable at the corner, but it's still a tame function. You can use SGD, and it will converge to a stationary point, a local minimum, if you use a certain decaying learning rate. But this result is very much unsatisfactory, even for a theoretician. Because what it says is, it just says that we converge to a local minimum. But that's not enough to understand why it is that deep learning works so well. Because deep learning works well in the sense that generalization performance is good. So if we converge to a local minimum, does that mean generalization is good? Well, certainly not. You could converge to a bad local minimum, and that probably happens sometimes, but in many cases, you don't converge to a bad local minimum in deep learning training. So this type of pure optimization theory is insufficient in addressing the question as to why deep learning works so well. We need to inject some information about the structure of deep learning in order to understand why deep learning works so well. If we just say we're minimizing functions, there's not much we can conclude. This theorem is a nice theorem, but there's not much we can proceed from here unless we take a model things more carefully, closely based on the structure of actual deep learning. So this leads to the field of NTK and universal approximation theory. First, let's talk about let's review the classical universal approximation theorems. So let's consider this function class and, excuse me. Let's consider this function class. So this function class, this sort of expression may feel a little bit foreign to many of you who study deep learning from an empirical perspective, but it's really just a two-layer neural network. It's a two-layer neural network. So here I'm drawing the diagram. There's an input of dimension d, and then there's a fully connected layer with width n, and then the output is a fully connected layer of width 1, and the output layer does not have any bias. So it's weight only for the output layer. And if you write that explicitly as a function with a summation, this is how you would express that, express a two-layer neural network. And the classical universal approximation theorems by Sybenko in 1989 states that, so here I wrote the universal approximation theorem in a more mathematical language, but what this really means is that a sufficiently wide two-layer neural network can approximate any continuous function. That's what Sybenko is saying. And in 1991, Hornick proved a similar result. This one states that any sufficiently wide two-layer neural network can approximate any function in the LP norm. So the uniform norm, in the sense of uniform norm, the sense of LP spaces, these are similar but slightly different notions of closeness. In any case, the line of universal approximation theory, it establishes that whatever reasonable notion of similarity within functions you choose, you can establish a universal approximation result, stating that a sufficiently wide two-layer neural network with a nonlinear activation function can approximate it. So these are nice, encouraging results from a theoretical perspective, but there is a crucial deficiency in these results, and that is that these are mere existence results. It does not tell us whether we can learn these approximations. In deep learning, we use data, we set up our model, and then we perform training via some optimizer to learn the neural network configuration. These universal approximation theorems, they do not say anything about whether things can be learned. It does not say anything about the trainability of these neural networks. So then, nearly 2 decades pass, and then Rahimi and Recht, they present their work on random feature learning. So the setup is similar. We'll again consider the two-layer neural network, but the setup they consider is they will randomly initialize the hidden unit weights and biases. The A's and B's in this equation, they will be randomly initialized as IID Gaussians with certain mean and variance. And then the output layer weights, the weights of the final fully connected layer, they will be trained. They will be learned through training. And in this setup, which is referred to as the random feature learning setup, training provably converges because training actually becomes a convex optimization problem. And the trained neural network has a certain nice generalization performance. They even have a quantitative result that is of order 1 over square root of n. So this is a nice result. It states that not only does the approximation exist, here is an explicit algorithm as to how you can find this approximation. There is a specific implementable training routine, training algorithm that you can use, and you have a theoretical guarantee as to how it will perform. So this is very nice, but here is the problem. This doesn't work very well in practice. Yes, there is the theory, and it does converge when n is very, very large, but works well when n is very, very large, but n has to be very, very large. In other words, the rate is 1 over square root of n, but there's a constant, and the constant is very large for practical applications. And what's a little bit sort of unsatisfactory when you actually implement this algorithm is that in order to implement this particular algorithm in, let's say, PyTorch or TensorFlow, what you will do is you will set up a two-layer neural network, and you'll declare the first fully connected layer the weights of the fully connected layer to be not trainable, and only the output layer weights to be trainable. But you do that first, and then perform the training, and then look at the output. And then if you go back, and then set the blue weights to actually be trainable, and then run the experiment again, it actually works better. So this gimmick of not training the hidden unit weights and biases, fixing the hidden unit weights and biases, it is only for theoretical convenience. If you actually train both layers, the performance improves. So there is a significant gap between the theory and the empirical observed practice, even in this simple two-layer setup. So people wanted a better answer to this, and especially with the explosion of modern deep learning, theory-minded folks, they came up with some very interesting theory around the year 2018, and the field of deep learning theory was born. So in 2018, several authors concurrently presented the mean field limit. And in the mean field limit, what they consider is they consider the limit in which the neural network is infinitely large. So in the prior discussion, what I was talking about wide two-layer neural networks. They are two-layer neural networks, and the width can be very, very large, but they're still finite. But in this theorem, I'm actually talking about infinitely wide two-layer neural networks. And what they showed is that the training dynamics of an infinitely wide two-layer neural network is characterized by the solution of this PDE. It's an instance of the continuity equation. And this PDE, it looks a little bit scary, but we can analytically, attractively characterize the solution, the dynamics of this PDE, and that will allow us to establish provable trainability guarantees for infinitely wide two-layer neural networks. Finite two-layer neural networks are difficult to analyze. But if we consider the infinite width limit, in the infinite width limit, the analysis actually becomes more tractable, more simpler. And in the infinite width limit, we can prove that training will succeed. In 2018, there was another landmark result called the neural tangent kernel. And this is a different kind of limiting regime, but this result states that if you have the training dynamics of a depth L neural network, not just 2, but L can be arbitrarily deep, and if you let the width of these hidden layers go to tend to infinity, then the network becomes essentially linear in the infinite width limit, and if you use a convex loss function, and loss functions used in deep learning are mostly convex. People often use the means, the MSE loss or the cross entropy loss. These are convex losses. So if you use this infinitely wide neural network with those common convex losses, then training becomes a convex optimization problem, and you can establish provable convergence guarantees. Okay. So this, the work that I'll present builds on the NTK theory, the neural tangent kernel theory. So let me give a very brief outline as to how the theory is built. So let's consider the optimization problem, the training problem of minimizing performing this empirical risk minimization, and we'll train using stochastic gradient descent. The NTK theory is based off of two key insights, two simplifications. The first simplification is that instead of considering stochastic gradient descent, we'll consider gradient flow. And gradient flow, it considers the training dynamics in a continuous time limit rather than a discrete time for loop. So the iteration index k is now replaced by a continuous time process. And this is a good approximation when the step size alpha is small. When the learning rate is infinitesimally small, when the learning rate is very, very small, then we can approximate SGD via this gradient flow. Okay, and then the second key insight is that we'll consider not the evolution of the parameters, but actually the evolution of the function. So when you perform training in deep learning, in PyTorch, in TensorFlow, you have your parameters, and every iteration, every epoch, you update the neural network parameters. But in this theory, let's not look at the parameters, because in the end, the parameters is not what we actually care about. What we care about is the prediction function. So instead of looking at the change, instead of looking at d theta dt, how does theta change over time? Instead of looking at that, let's look at df dt, where f is our prediction function that uses theta as its neural network parameters. And when we translate the training gradient flow, or SGD dynamics, imposed on theta, if we translate that to the function, then, and that translation is done via the chain rule and some calculations, then our training dynamics can be expressed as a gradient flow in the function space, preconditioned by the neural tangent kernel, written here as big theta. So this big theta is referred to as the neural tangent kernel, and it acts as a linear operator in the space of functions. Okay, so then the model that we will be analyzing is was initially analyzed for neural tangent kernel is the deep multi-layer perceptron. This is where people started, and then people then also considered deep convolutional networks as well. So this is the most basic form of the Deep Mlp. And the neural tangent kernel theory, the very initial version of it, states that as the width of the neural network becomes infinite, then the neural tangent kernel, which characterizes the training dynamics in terms of the function, it becomes simple. And I won't exactly explain what I mean by simple, but the neural tangent kernel, as the widths become infinity, it becomes time independent, which is actually a crucial component in preserving convexity. And also, we get a nice analytical formula. So this limit, this theta infinity, is something we have a nice analytical formula. We have a very specific understanding of what the limit looks like. So the consequence of this theory is that when we use a convex loss function, the training neural networks, deep neural networks, it reduces to a convex optimization problem. And this is, in my view, very beautiful. It's a very beautiful line of research, beautiful result. But here's a limitation of this result. It considers neural networks in the limit where depth is bounded and the width becomes infinite. But we all know that in the modern success of deep learning, depth plays a crucial role. After all, the field is called deep learning. So what role does depth play in deep learning? Well, in my view, the neural tangent kernel theory does not adequately address the question of what is the importance of depth in deep learning. It tells us what happens when we have sufficient width, but it does not tell us what happens when we have a sufficient depth. So because of this concern, people have started, in recent years, have started to analyze deep neural networks rather than wide neural networks. So the classical universal approximation theorem considers the universality of infinitely wide neural networks. But what about infinitely deep neural networks? So there are many now universal approximation results for deep narrow neural networks. There's a result by Kitzer and Lyons and another by Professor Shin's group at KAIST. And they basically establish that MLPs with a certain narrow width and infinite depth is dense in the space of continuous functions. It can approximate any continuous function. So again, these are nice encouraging results, but these are, again, mere existence results. They do not tell us anything. They do not say anything about whether these configurations, these approximations, can be found through training. Okay, so then I'll now move on to presenting our line of work. So our work, again, is entitled NTK Analysis of Deep Narrow Neural Networks. And what we'll do is we will propose a certain neural network architecture and an initialization scheme for deep neural networks and establish that they provably converge. So the neural network architecture will be a depth L MLP, a multi-layer perceptron, a ReLU MLP. So the architecture, I perhaps should have described it. The architecture is just a ReLU MLP with a fixed width. So it's ReLU, it's fully connected layer ReLU, fully connected layer ReLU, that's repeated L times. It's the simplest possible deep MLP architecture. And we'll consider the limit in which the depth becomes infinity. The architecture is going to be, as described, very standard. The initialization, however, will be actually very particular, very much non-standard. So we'll initialize the weights via this description. It's too much to read during this talk, so I'll move on. I'll show you this illustration. So this is the illustration of the Deep Mlp. And so here, the solid lines, in this illustration, the solid lines correspond to weights initialized as 1. The dotted lines correspond to weights initialized as IID Gaussians, and the empty lines, the lines not drawn, those correspond to weights that are set to be equal to 0. The point that I wish to make in this very brief description of this illustration is that the architecture is completely standard, and although the initialization scheme is non-standard, it's not that complicated, and it's also very much implementable. It's not something that just merely exists. This initialization is something you can do, and we actually do this. So we have some brief experimental results, and this is something that is very much actionable. It's algorithmically, we can do this initialization. And our main result is as follows. So under this set initialization, the training dynamics of this infinitely deep MLP with this width, it provably converges. So we show that in the infinite width limit, this neural network is trainable provably. The proof of this result characterizes the NTK in the infinite width limit, and the very high level roadmap of the proof is similar to the prior NTK analyses of infinitely wide neural networks, but there is a crucial difference, the difference being we consider the infinite depth, whereas prior work considered infinite width. And that difference bears a key technical challenge, and that is that controlling the invariance of the NTK is much more technical in this infinite depth limit, because our analysis requires controlling an infinite product of matrices rather than an infinite sum of matrices. So if you have an infinite sum of random things, then you can control it theoretically by using the law of large numbers or the central limit theorem, and that's how it's done in the prior NTK analyses. But for us, we don't have an infinite sum of random things. We have an infinite product of random things. And infinite products of random matrices, that's a much more tricky thing to control. So now our initialization scheme and our theory also extends to CNNs as well. So again, we'll consider a CNN with this very particular initialization, and I show the initialization scheme in equations just for the sake of completeness. But here's the illustration. So again, these solid lines, they correspond to neural network CNN filters. So these are 3 by 3 convolutional operations, and the solid lines correspond to the convolutional operations initialized as identity. So we use 3 by 3 convolutional filters, and we use a padding so that the spatial dimension is preserved. And the architecture is convolution, ReLU repeated L times. The dotted lines correspond to filters initialized as IID Gaussians, and the empty lines correspond to filters initialized as 0. Okay, and here is our main result. So we show that under this initialization, the training dynamics of this infinitely deep convolutional neural network with this particular width also provably converges. So this is a trainability guarantee. The proof of this result follows from basically the same line of argument as the MLP case. So I would basically say that this is essentially the same exact result, although if you were to look at the equations for the CNN becomes much more complicated because, as you know, convolutional filters in deep learning, they're indexed by 4 indices, so they're just the equation becomes much more complicated because you need to keep track of all the different indices, but the core insight that goes into the proof is exactly the same as in the MLP case. Okay, so we had some brief experiments to validate our theory. So we trained a depth L MLP on a certain toy function, And on the left, you can see that the true function and the trained neural networks, they are basically the same. So this is an indication that training succeeds. So when I say training succeeds, what I mean is that the training loss converges to 0. So plotting the training loss is one way we monitor whether actually training succeeds, but looking at the actual prediction function in this toy example is another way we verify that training does indeed succeed. On the figure on the right, we train depth 100 and depth 10,000 MLPs, and we observe that as the depth grows, the randomness and the variability throughout training diminishes. So here, if you take a look, the red lines, they correspond to depth 100 MLPs, and at initialization and after a certain amount of training, the kernel values, a certain property of the neural network, they change a lot. They move around a lot. There's a lot of variation. The theory predicts that as the depth L grows, there will be the initialization will be less and less random, and the kernel will change throughout training less and less, so there should be much more stability. And if you look at the green lines, that's the solid green lines are at initialization, the dotted green lines are the kernels after 2,000 iterations of training. You'll see that they all overlap very well, so there is much less randomness, randomness and variation throughout training, as the theory predicts. Here's another experiment. So we, in this work, we considered this very particular initialization, standard architecture, but unusual initialization. So we thought, okay, what if we use the standard initialization and try to train? Well, first, we tried our initialization and trained it, and we observed that training works. So we considered a depth 1,000 MLP, depth 1,000 CNN. We train, and training loss diminishes to 0, and we haven't reached 0, but if we continue the epochs, it will certainly go to 0. We can see that the training loss diminishes in the black curves. But then we kept the same architecture, but we tried the standard Kai-Ming-He initialization for both the MLP and CNNs, and then we tried to train, and we get the red curves. We have multiple red curves because we did a grid search on the learning rates, and it didn't matter what learning rate we used, we were not able to adequately reduce the training loss. So with the standard Kai-Ming-He initialization, training failed all the time. With our initialization, training did succeed, as the theory predicted. So let me conclude. So prior work in this area analyzed neural networks in the infinite width limit, or in the limit in which the width becomes infinite first, and then we consider, and then they consider the limit in which the depth then becomes infinite. So this limit, this sequence of limits where we have a lim of width first and the lim of depth first, and the depth second, this is, you can think of this as the limit in which the width is much, much larger than compared to the depth. In our work, we provide the first trainability guarantee for neural networks in the limit in which only the depth becomes infinite. So for our results, the width is bounded. The width is fixed. It's basically the number of inputs plus the number of outputs. It's a fixed width, and then only the depth becomes infinite. And in future work, we plan to continue studying the large depth neural networks. So we would like to study the limit in which the depth and limit goes to infinity together, or maybe the limit in which the depth becomes infinite first, and then we have then the width becomes infinite. So this would be the limit in which the depth is much larger than the width. And in our undergraduate calculus courses, you've all sort of encountered the distinction between the limits, so the order of two limits. So the limit in which the width becomes infinite and then the depth becomes infinite, it's not the same as the limit in which the depth becomes infinite and then the width becomes infinite next. So the order of the limits do matter. And the qualitative difference would be that deeper versus wider, this is the limit in which networks are deeper, this is the limit in which depth networks are wider. And the goal in pursuing this type of theoretical work is that these limits will provide better insight as to why deep learning exhibits the remarkable performance. As I've described, as I've mentioned, We all know that deep learning has produced remarkable empirical results. We have from a theoretical perspective, we have a pretty good understanding as to why wide neural networks perform very well. But as the question of why deep neural networks perform well, that remains an open question. And I hope to continue to study that area. Okay, so that concludes my talk. Thank you, everybody, for your attention.